So welcome everybody to round 2 of the Algebra, Particles, and Quantum Theory seminar series. I'm grateful to be able to introduce to you tonight's speaker, John Baez. John started out in mathematics at Princeton University, where he completed a thesis with the rather intriguing title, Recursivity in Quantum Mechanics. He then went on to do a PhD at MIT with supervisor Irving Segal. Fast forward a few years, and John is now based at UC Riverside and maintains affiliations with the Center for Quantum Technologies in Singapore and the Topos Institute in Berkeley. In mathematical physics, John is knowledgeable in perhaps an unparalleled number of topics. In fact, it would be more efficient to list the topics that he hasn't written about. A quick search through his list of co-authored books or his blog Azimuth or N Category Cafe, which he co-founded, shows John's extensive works on algebraic and constructive QFT, loop quantum gravity, higher category theory, applied category theory, quantum techniques for stochastic mechanics, quantum foundations, and countless others. He is the author of the classic paper on division algebras entitled The Octonions, which serves for many of us as our first point of reference on the subject. Together with John Huerta, John Baez won the Levi L. Conant Prize for their paper, The Algebra of Grand Unified Theories, which is a paper that I feel every self-respecting particle physicist should know about. Tonight, John will be telling us about the 10 real associative superdivision algebras and how their ghostly figure materializes in the context of Clifford algebras and Bott periodicity, and within the characterization of 10 different types of matter based on discrete symmetries. His talk is entitled The Tenfold Way. Now, typically before a seminar, I like to encourage everyone to ask questions throughout the talk, especially students. However, today's crowd is a bit larger than usual, so it would be helpful if you could please ask only clarification questions during the talk, and it will be fair game to ask more expansive questions after John's talk. Okay, so John, anytime you're ready.
Okay, I'm ready. Well, thanks very much for the invitation. It's great to have a chance to speak about this subject. So I've been thinking about the tenfold way for a while, and I've developed maybe too much to say about it, so I'll focus on just a portion of this idea. So there are 10 different ways that Hamiltonians can get along with time reversal and charge conjugation symmetry, and I'll explain those 10 ways. There are also 10 associative real superdivision algebras. You may know about the plain old fashioned real division algebras, which are the real numbers, the complex numbers, and the quaternions. So those are 3 of these 10 guys, but I'll explain this more general concept in my talk. There are 10 Morita equivalence classes of real and complex Clifford algebras. You may have heard of Clifford algebras, and you may know that real Clifford algebras have this period 8 phenomenon, so that there are really only 8 truly different kinds, and then after that they sort of repeat and get bigger and bigger in a predictable way. And there are 2 complex Clifford algebras, 2 Morita equivalence classes of them. So 8 plus 2 equals 10, and believe it or not, that's connected to these other 10s. And there are also 10 classical families of these highly symmetrical spaces studied by Cartan called compact symmetric spaces. And it's really a mystery to me why those 10 classes perfectly line up with these other 10 things, although it's not a mystery to me how you get symmetric spaces from these other things. Unfortunately, I won't really have time to talk about that. And the whole subject of the tenfold way showed up in condensed matter physics, where they have various classifications of states of matter or types of Hamiltonians for systems of free fermions, for example, which give other ways to get at this tenfoldness. And even though that's like the most physical aspect, in some ways, that is the most practical physical aspect, I won't really talk about that at all. So the physics in this talk will be mostly about the first bullet point here. Okay, so let's start from the beginning, and I'll start from something simpler called the threefold way. So in fact, I'm going to try to take a pretty elementary approach and start with some stuff about quantum mechanics. some of which you all know, and some of which you may not know, but you should know. So I'll tell you. So we use unit vectors in a Hilbert space to describe pure states in quantum mechanics. I'm only going to be talking about pure states. I'll just say states, I guess. And what you can do with them, for starters, is calculate the transition probability. You put a system in state phi, you measure whether it's in state C, you find it sometimes is and sometimes isn't. The probability is the absolute value of the inner product of those two states squared. And that probability doesn't change if you multiply either psi or phi by a phase, that is a unit complex number. So people figured out pretty early on that pure states in quantum mechanics are really given not by unit vectors, but by equivalence classes of unit vectors, where you say two unit vectors count as the same if they differ by a phase, or maybe differ is a misleading word, if one of them is the other multiplied by a phase, a unit complex number. So really we should work with these equivalence classes. And one of these equivalence classes is a point in what's called the projective space of our Hilbert space, or pH. So that nuance there is very, very important. It manifests itself in many ways in physics. And one of them is in Wigner's theorem, which I guess goes back to around 1931, which says, suppose you have a Hilbert space, and then suppose you have a map from the projective space to itself that preserves transition probabilities, so that if you apply this map to these equivalence classes, you get new equivalence classes where the transition probabilities between them are the same. So that would be like the physically significant sense of symmetry, a map that preserves transition probabilities. And he concludes that any such map comes from either a unitary operator, and then you go, yeah, I know about those, or an anti-unitary operator, and that's slightly more interesting. So a unitary operator just preserves everything, addition, multiplication by complex numbers, and the inner product, whereas an anti-unitary operator preserves addition, but it's an anti-linear operator, meaning that if you pull a number, a scalar through it, it comes out with a complex conjugate. And also it doesn't preserve the inner product, it takes the inner product and complex conjugates it. So this raises the possibility that symmetries in physics can be described either by unitaries or by anti-unitaries, and that real possibility really occurs. And you can see it very clearly if you focus your attention on the simple case of some discrete symmetries, namely symmetries that square to 1. And there are three super famous ones of those. Parity, which is sending each point in space to its negative, and so it's turning left-handed people into right-handed people and vice versa. Charge conjugation would be turning, I guess, since I'm talking about people made of matter into people made of antimatter. Or in condensed matter physics, there are systems where you have particles or holes, absences of particles, which act like particles themselves. And although Dirac's theory of antimatter was that antimatter was holes, we don't really exactly think of antiparticles in quantum field theory as holes anymore, but in condensed matter physics, holes are a real thing. So it's like semiconductors sometimes carry current in the form of holes. And so charge conjugation is a symmetry that may or may not exist in a particular system, which switches particles and holes. And then time reversal, switching the direction of time, for example, flipping the velocity of a particle to its negative. So systems may or may not have any one of these symmetries, and they also may be symmetric just under certain combinations of these symmetries, which you could call CP, PT, CT, or CPT. Those names are probably a little bit misleading for what I'm doing, because what I'm saying is that you may have a physical system which does not have C symmetry and which does not have P symmetry. So technically CP doesn't make sense, but it may be symmetrical under the combined operation of switching particles and antiparticles, and also parity, for example. Right. So let's think about what can happen with these symmetries that square to 1. So suppose you've got a map from the projective space to itself that preserves transition probabilities, and if you do it twice, you get back where you started from. So Wigner's theorem says there's got to be two options. That either comes from a unitary or an anti-unitary. But because this symmetry squares to 1, that means that if it came from a unitary, that unitary would square to some phase, because of any phase acts as the identity on the projective space. And if it came from an anti-unitary, well, then you'd have an anti-unitary that when you square it, you get a phase. But they're very different. These possibilities behave in a very different way from each other. Because in the unitary case, if you have u squared equals some phase c, then you can just adjust your unitary by multiplying it by an appropriate phase, namely c to the -1/2 power. Now you have a new unitary, which squares to 1 again. And because this new unitary differs from the old only by a phase, it has the same effect on the projective space. So it has the same physical effect. And we've just managed to conveniently get it so that it squares to 1. So in other words, in the unitary case, you may just as well assume it squares to 1 without loss of generality. But the anti-unitary case, that's not true. Because for the anti-unitary operator, if you try the same trick of adjusting it by a phase, that doesn't change the square, because when you pull the phase through one of those j's, it switches to its complex conjugate. And you just get c times c bar, which is 1. So you're stuck with this phase in the anti-unitary case. But the interesting thing is the phase can't be just any old phase, because you can do a little calculation here. See, we know that if we pull this phase through j, it comes out complex conjugated. But we also are assuming that j squared is equal to this phase. But j does commute with j squared, because any power of anything commutes with itself in this associative world here. And so the phase also does commute with j. So we get these two equations, one saying it commutes with a complex conjugate and the other that it just commutes. And the only options are that c is its complex conjugate, which for a phase means it's plus or minus 1. So we can't just get any old phase. It has to be plus or minus 1. So in other words, we've got three basic options for symmetries that square to the identity. They can come from a unitary, in which case, without loss of generality, we may well assume it squares 1. But if it's implemented by an anti-unitary, then we have two choices, j squared equals 1 or j squared equals minus 1. So the anti-unitaries are much more exciting than the unitaries from this point of view. And that's where I'll be focusing my attention. Now, these two cases are really interesting for a bunch of reasons. For one thing is, suppose you have an anti-unitary that squares to 1. Well, that reminds you a lot of complex conjugation. Complex conjugation is an anti-unitary map from the complex unit numbers to themselves that squares to 1. And so you can do tricks with any such j that are like you would do for complex conjugation. In particular, you can focus your attention on the vectors that are preserved by this j, and they will form a real vector space. That is, they'll be closed under multiplication by real numbers, and it's actually a real Hilbert space. There's a perfectly fine concept of a Hilbert space over the real numbers, and that's what this real part will be. And your original, so I'll call that H sub r, and the original Hilbert space is just the complexification of that real Hilbert space. In other words, any vector in the original Hilbert space is just a linear combination of two vectors in your real Hilbert space, a real part and an imaginary part. So it would be like a times one of these guys plus ib times another one of these guys. Just like the complex plane is the complexification of the real line. So there's an underlying real Hilbert space structure in this situation. And if your anti-unitary squares to minus 1, then it turns out there's an underlying quaternionic structure. Because in that case, you can take these operators, take ordinary multiplication by I, make up a new thing called j, which is this anti-unitary j, and then the product of those two, which we'll call k. And if you do a few calculations, you see that these three operators, I, j, and k, obey the usual relations for the quaternions, which Hamilton scrawled on a wall in Dublin, I guess. And so what we're getting here is that you have now ways to take vectors in your Hilbert space and multiply them, not just by complex numbers, but by quaternions if you want. And so thus you can make your Hilbert space into a quaternionic Hilbert space. Now those are a little more obscure than even real Hilbert spaces, but in fact the theory of Hilbert spaces works pretty darn well for quaternions as well. And so I mean it. And so then what's going on is that your original Hilbert space is what you'd call the underlying complex Hilbert space. In other words, the Hilbert space where you just forget about J and K and just only think about multiplying by complex numbers. If you want to think like an algebraist, you've got this quaternionic Hilbert space. That's a left H module, but because the complex numbers are contained in the quaternions H, then you can tensor over C with complex numbers, and you get a left C module, namely an ordinary complex vector space. If you don't know what all that stuff means, it's just a fancy way of saying that, like, we're forgetting that we can multiply by quaternions and only thinking about multiplying by the complex numbers. But I wrote it in this way to make the analogy with the previous slide more sharp. So the real numbers, the complex and the quaternions, all show up in quantum physics. I had been wondering for years, why did nature pick to use complex Hilbert spaces instead of these other two? And then eventually I realized that it actually has picked all three. They're all there. So why are those three guys special? Well, you probably know, or at least some of you probably know, but I'll come out and say it here. So I'm going to say the word algebra a bunch of times, and I always mean a finite dimensional real algebra. So it's a real vector space with an associative product that distributes over linear combinations, and it has a unit, one multiplicative unit. So then with all those caveats, a division algebra is going to be, for me, an algebra where any non-zero element has a multiplicative inverse. Notice I'm assuming that it's associative. I love the octonions, but that's not what today's talk is about. And so I don't want to keep saying associative algebra. That's the only kind I'm talking about today. And so then Frobenius, I guess sometime around 1898, maybe, I forget, proved that there are exactly three division algebras: the real numbers, the complex numbers, and the quaternions. So we're seeing those all showing up naturally, starting from a traditional attitude of purely complex quantum mechanics, but carefully analyzing what symmetries should be, that symmetries do not necessarily need to be linear, they're just maps on the projective space that preserve transition probabilities. And then we see that all these three number systems show up from that very physical assumption. And the role of the division algebras in quantum physics becomes even clearer if you focus on systems that have extra symmetries. In other words, not just a bare Hilbert space, but a Hilbert space on which some group is acting as symmetries. Now, I've just told you that symmetries could be unitary or anti-unitary. So a detailed study of this would go into both of those on this slide here. And actually, I urge you to read Gregory Moore's lecture notes about this whole subject, where he considers the anti-unitary case here as well. But anyway, I'm just going to talk about unitary representations of groups right now and how they interact with these anti-unitary operators that I was just talking about. So a unitary representation of a group on a Hilbert space will be one unitary operator for each group element, in a way that when you multiply the two group elements, those operators multiply, and the operator for the identity in your group is the identity operator. So your group is acting as unitary transformations on your Hilbert space. And the simplest of the representations are the ones called irreducible, which are the ones where the only closed subspaces that are preserved by all the group elements are the zero-dimensional subspace and the whole Hilbert space. For unitary representations, you can show that a representation is irreducible if and only if it's not the direct sum of two other representations. So you can think of the irreducible representations as the ones that can't be broken down any further. And they're sort of the building blocks of representation theory. And that's why they show up a lot when we're studying elementary particles. There's a funny analogy between elementary particles and irreducible group representations. It's more than just an analogy. We use the latter to describe the former. But what I meant is the analogies. We can try to like bust a particle into smaller particles by hitting it with a hammer or something like that. And here we're doing the same type of thing with a group representation. Okay, so Schröer had this amazingly powerful lemma that we use a lot that says that if you have an irreducible unitary representation of a group G on a Hilbert space H, then the only unitary operators on that Hilbert space that commute with all the group, with all the operators coming from your group, could be our phases, multiplication by a phase. So that's not many possibilities. So various other people, including Schröer, I suspect, studied what happens with the anti-unitary operators that commute with all the operators rho G. But the first person to, I think, write a really detailed paper about it was Freeman Dyson in the 60s. So, and he coined the term the threefold way. So I'm honoring him with this one here. So suppose rho is an irreducible unitary representation of a group G on a Hilbert space H, then there are three possibilities, which are mutually exclusive. So only one of these could be true, and one of them must be true. So there's either an anti-unitary operator with J squared equals -1 that commutes with all the rho G, or there's an anti-unitary operator with J squared equals 1 commuting with all the rho G, or there's no anti-unitary operator commuting with all the rho G. So the only thing you have to prove here really is that there can't be both an anti-unitary with J squared equals 1 and also an anti-unitary with J squared equals -1 commuting with them. That makes this then into a trichotomy. So in the first case, or the negative first case, I'm going to call it, then what I've already shown you is that then rho is actually coming from a representation on a quaternionic Hilbert space. And so we call these, mathematicians call these representations quaternionic. So they're on a complex Hilbert space, but actually you could promote it to a quaternionic Hilbert space. In the other case where J squared equals 1, then we've seen that rho, we've seen that you can find a real Hilbert space hiding inside your complex Hilbert space, and rho will actually preserve that real Hilbert space. So rho will be the complexification of a representation on a real Hilbert space. And in that case, we call our representation rho real, because it comes from a real representation. And in the third case, where neither of the two is true, then people use the slightly confusing term that they call it complex, meaning that it's just complex. There's nothing more you can do with it. It's just only complex. So there's this beautiful trichotomy here, and we see it in life. For example, what about the representations of SU2? So the irreducible representations of SU2, there's one for every spin J, and it turns out that in any one of those representations, all the transformations coming from SU2 do commute with some anti-unitary. Unfortunately, I'm calling this anti-unitary J. Now you're probably thinking about angular momentum in quantum mechanics, especially if I write J squared, and I probably should have not called it J, but it was irresistible because of the connection to quaternions. So there are two possibilities. One is that J squared is equal to the identity, and that happens when your spin is an integer. And the other possibility is that J squared equals -1, and that happens when the spin is a half integer. So for example, the spin 1 representation of SU2 is a representation on the complex vector space C3, just the complexification of a representation on the space R3. So if you work it out, you see that SU2 is just preserving R3 sitting inside C3. And that's not surprising because in this particular case, the way SU2 is acting is really just as ordinary rotations on R3. And then you complexify it and you get C3. So that's what's going on there. And on the other hand, more excitingly, the spin 1/2 representation is a quaternionic representation. We normally think of it as a representation on C squared, but what I'm saying is that really you could think of that as coming from a representation on H. Both C squared and H have real dimension 4, but what I'm saying is that C squared is what you get when you take H and you forget how to multiply by J and K. And in fact, the way that SU2 is acting is incredibly beautiful because SU2 you can think of as the group of quaternions whose absolute value is 1. And so that those quaternions act on H, the quaternions, by right multiplication, and that commutes with left multiplication by the quaternions. So that's what makes it into a quaternionic representation. So who knew the Humboldt electron was a quaternion all along? So we find that this is a general thing for any representation that you can break up into irreducibles. We can apply this analysis to. So suppose you have a unitary representation of a compact Lie group. In that case, you can always break it down into a direct sum of irreducibles. And what we can do here is we can group those irreducibles into the quaternionic ones, take the sum of all of those, the complex ones, take the sum of all of those, and the real one. So we split our representation into a direct sum of 3 parts. We're able to do this in a canonical way without making any choices. And even more cool is the fact that this, now I'll finally explain why I call these 3 choices -1, 0, and 1. The set of these 3 numbers is actually closed under multiplication, if you think of them as real numbers, and it actually has this beautiful property that if you take 2 different unitary representations, their jth part, where j is -1, 0, or 1, can be computed from the various parts of the 2 things that you're tensoring. So we're getting this nice relationship here between tensor products and this grading of our representation into 3 parts. So this is an efficient way of saying things like, if you tensor 2 quaternionic representations, then you get a real representation because -1 times -1 is 1. If you tensor 2 real representations, you get a real representation. If you tensor anything with a complex representation, you get a complex representation because 0 swallows -1 and 1. And this is sort of the dominance of the complex numbers over the other 2 division algebras, which has something to do with why we probably think that quantum mechanics is innately complex. So you may have seen graded vector spaces. You probably haven't seen graded vector spaces graded by this monoid, which I'm calling 3. But this is an interesting innate structure in mathematics. So now what about 10? So the tenfold way is just an elaboration of this set of ideas. First, I'll start out with a physicsy way of thinking about it, and then I'll sort of move it over towards more of a pure mathematical way. So one way to think about it, that's sort of an application of the mathematical way, is to say that the tenfold way describes the options for charge conjugation and time reversal. In condensed matter physics, we assume that those are commuting anti-unitary operators on the single particle space. So time reversal symmetry, it squares to 1 physically. So that means by our analysis that as the anti-unitary operator, it must either square to 1 or square to -1 if your system has time reversal symmetry. But there's another possibility that your system just doesn't have time reversal symmetry. It's just not symmetrical in that way. Similarly, with charge conjugation symmetry, it could square to 1 or -1, or you could just not have it at all. So that's 3 times 3 different options for how these symmetries could behave or not exist at all. So that's 9, but there's a 10th, which is that it's possible that you may only have the combination of both time reversal symmetry and charge conjugation symmetry. We could call that CT, but that would be misleading. That would be misleading since we don't have C and T separately. So they call it S, and that one will be unitary. And so we've seen you can assume that its square is equal to 1. So we get a total of 10 options. Okay, that's one way to think about it. And that makes it sound like you need to know about things like particles and antiparticles and time reversal to get this stuff happening. But in fact, it's even more fundamental than that. It happens whenever you have your Hilbert space chopped into two parts. So a super Hilbert space is just a Hilbert space that's written as the direct sum of two parts, H0 and H1, which we call even and odd parts. So we could call states even if they're in H0 and odd if they're in H1. Now, there are different applications of super Hilbert spaces. And if you hear the word super and you're a physicist, you may be thinking, oh no, now we're starting to do supersymmetry. Or you may be thinking, yay, now we're finally starting to do supersymmetry. But in that kind of application, what we would be doing is we'd be letting H0 describe bosonic states and H1 describe fermionic states. And that's perfectly fine application of the math I'm going to talk about. But in fact, in condensed matter physics, that's not the main way. I've never even seen them try to use it that way. That's not the main way they apply this idea of the super Hilbert space. What they do instead is they think of H0 as a space of particle states, states of a single particle. So we're not doing second quantization here, right here. And H1 is a Hilbert space for antiparticles, or holes, actually, they would call them holes. And sometimes the way this happens is that you have some dispersion relation where momentum and energy are related as graphed by this hyperboloid. And then you'd say, okay, the states up here, we'll call them in H0, and the states down here, we'll call them in H1. So when you have this situation, and you start studying anti-unitary operators in this situation, there are two especially nice kinds of anti-unitaries. There are even ones, which map H0 to H0 and H1 to H1. And then there are odd ones that switch H0 and H1. There are also anti-unitaries that just completely mix up H0 and H1 in a messy way, but these two are particularly nice. So we're going to get a more refined classification of anti-unitaries in this situation where we have a graded Hilbert space or a super Hilbert space. And I'm going to think about symmetries as well. So I'm going to have a symmetry group running around, but I'll let it be a Z mod 2 graded group. And that just means it's a group that's a union of two disjoint subsets. So we say there are even elements and odd elements, and having the property that if you multiply an even guy and an even guy, you get an even guy, or if you multiply an even guy and an odd guy, you get an odd guy in either order, or if you multiply two odd elements, you get an even element. So we're doing addition mod 2 here in this, which is why it's called Z mod 2 graded. So then people will talk about a unitary representation of a Z mod 2 graded group on a super Hilbert space. So it's just an ordinary unitary representation, but it has the property that it gets along with these gradings. So if G is in Gi and psi is in Hj, then when you apply rho of G to psi, you get a vector in Hi plus J, where we're adding mod 2. So in other words, some of your group elements will be even, and they will map even vectors to even vectors and odd vectors to odd vectors. And some of your group elements may be odd, and they will switch even and odd vectors. So we can talk about irreducible unitary representations of this kind, but we change the definition now. Now, what we want to say is that the only closed subspaces that are the direct sum of an even part and an odd part and are preserved by all the group elements are 0 in the whole Hilbert space. So we're putting a restriction on the subspaces that need to have this property. This is a weakening of the usual concept of irreducibility, because there could be other weird subspaces that aren't of this form that are preserved by all the group elements. So now we get the tenfold way when we study irreducible unitary representations of a Z-mod 2 graded group for Hilbert space. We discover that there are now 10 different kinds, and they are classified in the way similar to the threefold way, but I'm going to formalize it a little bit more. We're going to look at the commutant, which means the set of all operators that commute with all the rho G. But here I mean real linear operators, because not necessarily complex linear, because I want to allow anti-unitary operators into the game. And so it turns out that you get these following options. So there may be an even unitary operator that commutes with all these rho of G's. And then it could have t squared equals 1 or t squared equals -1. Or maybe there's no such anti-unitary. And there may be an odd anti-unitary that commutes with all these rho sub G's, and it could square to 1 or -1. Or it might not exist. So we get 9 options from considering whether we have even or odd anti-unitary operators that commute with all these rho sub G's. And then finally, there's a 10th type where there aren't either of those two, but there's an odd unitary operator that commutes with all the rho of G's. And we can assume without loss of generality that S squared is equal to 1. Notice we always get phases that commute with everything, with all the rho sub G's. Phases will commute with all these rho sub G's, but they will be unitaries, not anti-unitaries, of course, and they will also be even because they map H0 to itself and H1 to itself, because they're just phases. So the interesting classification arises from thinking about the possibilities of either anti-unitaries that commute with all the rho sub G's or odd unitaries. Of course, if we have T and C, we can then go ahead and multiply them, and we will get an odd unitary that will act like this S. But we may also have this S without such a T or C. So we get these 10 options. And in condensed matter physics, people have gone through and tried to make physical systems that have all 10 of these behaviors. And if I had more knowledge, I would like to rattle off a bunch of examples of different systems with each of these 10 behaviors, or at least a bunch of these 10 behaviors. Some I don't think I've seen in the literature actually showing up yet in real life. But like the threefold way, what's going on here is that we really have a set of 10 options, and I'll call this set X because I'm going to go medieval, or actually go Roman on you, and call it X. And what you can see from what I've just said is that if you have a unitary representation of a Z-mod 2 graded group on a super Hilbert space, if it is a direct sum of irreducibles, for example, that would happen if G was compact, you can always split up that representation into a direct sum of irreducibles of the various 10 types that I've described. So if you let rho of I be the sum of all the irreducibles of the I type, then rho will be the sum of these different pieces, rho sub I. And then the cool part is that there's a way to add elements of this 10 element set that makes a formula true similar to the formula I showed you for the threefold way. For the threefold way, that set, which I called 3, was conveniently thought of as just the numbers -1, 0, and 1. And then the operation was nice to call it multiplication because it just happened to work out just fine. Here, it's probably a little more convenient to call this operation addition. That's just sort of a terminology thing. So in other words, to get the jth piece of rho tensor rho prime, you run around looking for all I and I prime that sum up to J, and you take the ith piece of the first representation and the I prime piece of the second representation, and you tensor them. This addition on the set X makes it into a commutative monoid. It's not a group, just like our 3-element set was not a group, right? 0 had no inverse. So we don't, it's not a group, but it's a commutative thing with an associative multiplication, associative and commutative multiplication. So what is it? Well, it's the disjoint union of the group Z mod 8, which has 8 elements, and the group Z mod 2, which has 2 elements. How in the heck do you add an element in Z mod 8 and an element in Z mod 2? Well, for starters, if you have 2 elements that are both in Z mod 8 or both in Z mod 2, you add them the usual way. You just addition mod 8 and addition mod 2. So the weird part is adding a guy in Z mod 8 with a guy in Z mod 2. So then what you do is you add them, but then you do it mod 2. So because 8 is divisible by 2, that's a thing that makes sense, to take a guy in Z mod 8 and look at what it is mod 2 and get a guy in Z mod 2. So for example, let me do some examples. I'm going to give names to these guys. I'll call the first 8 0 through 8. Well, let's see. I guess I can't count though, but it should be 0 through 7 because we're working mod 8. So 8 is the same as equal to 0. I guess this is technically true, but you have to remind you that 8 is the same as 0. But that was a mistake on my part. And then the other 2 guys, the guys in Z mod 2, I guess I'm going to use boldface for them and call them 0 and 1 with boldface. You can't pronounce a boldface any differently than a normal number. So 2 plus 3 is 5. But then 1 plus 1 is equal to 0. That's adding Z mod 2. But then the interesting case is something like this. So we do 6 plus 1. So that would be 7 maybe, but we take it mod 2. And so we get 1. So this, you can check, gives you a commutative and associative operation on this 10-element set. That may not be instantly obvious, but it's a fun little exercise.
Is there a straightforward way? Sorry, can I ask a quick question?
Sure.
Is there a straightforward way to see how the monoid relating to the threefold way kind of fits inside of the monoid related to the tenfold way?
Yeah, there is. I think the easiest way is to show you this picture, and then so here I'm showing the tenfold way picture, and in a second I'll show you where which ones are the ones. The threefold way is a sub thing of this tenfold thing. So here are the options. So here's 0 up through 7. So those are the ones in Z mod 8, and then this boldface 0 and 1s are the 2 options in Z mod 2. And so for each one, I'm telling you whether there is or is not anti-unitary operator C or T, and having squaring to 1 or minus 1. So 0, boldface 0 is the one where neither C nor T exist. Boldface 1 is where only the sort of the combination exists, which we're calling S. And so the threefold way sits inside this one as 0 and boldface 0 and 4. So it's sort of down the vertical here. So this T squared is the thing that in the threefold way I'd been calling J squared. So if I called this TJ, it would be more evident that we're sort of doing the same thing there. We're not having any C running around. We just have one even anti-unitary, I guess, is what's going on. It could square to 1, or it could square to -1, or it could not be there at all. So that's the threefold way. So it takes some calculating to check that, like if I have a Hilbert space with operators having these properties and a Hilbert space with operators having these properties, and I tensor them, I get a Hilbert space with operators satisfying these properties. But you can check that type of stuff. It's sort of subtle actually, but it's a calculation of some sort. So now, just as that set 3 turned out to be the set of the 3 division algebras, the set X, or 10, or whatever you want to call it, is secretly the set of the super division algebras. What the heck is a super division algebra? So it's a super algebra. That's an algebra that's written as a direct sum of 2 pieces, which we'll call an even and an odd part. which has the property that multiplication respects that grading. So an even thing times an even thing is another even thing, and even times an odd is an odd. Product of two odds is even. And then a super division algebra is a super algebra where any non-zero element that is either even or odd, so that it completely lives in one or the other of these two pieces, has a multiplicative inverse. So there again, this clause here is weakening the usual condition on a division algebra that says that anybody who's not zero has a multiplicative inverse. Here we're saying only the ones that are what you call homogeneous, only the ones that actually live in one of these two pieces has to have a multiplicative inverse. So that's how we get to have more superdivision algebras than we had division algebras. So there are 10 superdivision, I'll tell you 10 superdivision algebras in a minute, but just to like get you revved up, you could take the ordinary complex numbers and make it into a superdivision algebra in two different ways. It's a division algebra, okay? We know it's a division algebra, but when you make it into a superdivision algebra, you have to say what's even and what's odd. And so you can make everything even, and that would be one way to get a superdivision algebra. But there's another way where you take the real numbers to count as even, so the subspace of real numbers is even, and the subspace of imaginary numbers you take to be odd, and then that indeed has this kind of property here, right? Like imaginary times imaginary is real and so on. So those are distinct superdivision algebras, even though they both come from the same division algebra. So that's basically the part of the trick for how we get so many of them. I'm not sure really who classified the 10 superdivision algebras. So CTC Wall definitely did a huge amount of work in discovering this stuff. And then later on, Deline wrote a beautiful paper laying out the classification of the 10 superdivision algebras. And there may be other people involved who deserve credit here, but this is the theorem that there are 10 of them. So here they are. So amazingly, they are all Clifford algebras. Well, Cliff 0 is a very boring Clifford algebra. It's just the real numbers. And I'm going to treat it as a superdivision algebra where every element is even. Cliff 1, now we're starting to get into some actual exciting Clifford algebras, but it's not all that exciting. What we're going to do is we're going to take the real numbers and we're going to throw in a square root of -1. That sounds awfully like the complex numbers. Yes, it is the complex numbers, but we're going to throw in an odd square root of 1. That is, we're going to treat I as an odd element of our super algebra. So this is complex numbers, but where the imaginaries are odd. Now we're really getting to Clifford algebras here. Now we're going to take the free superalgebra on two anti-commuting odd square roots of 1. So we take two square roots of -1, treat them both as odd, and we get a superalgebra that way. And that's the quaternions, but it's the quaternions where you could say like I and J are odd, and then K, which is their product, is even. So you can keep on throwing in more square roots of -1, and we're throwing in odd square roots of -1. So we think of the Clifford algebra as a superalgebra in that way. So Cliff 3 will have 3 anti-commuting odd square roots of -1 thrown in, and then we let them freely generate a superalgebra. And this, as an algebra, is isomorphic to a direct sum of the quaternions with themselves. So this is an algebra that would not be a division algebra, but we can treat it as, but it is a superdivision algebra. We could have thrown in square roots of +1. So we could look at the free superalgebra on an odd square root of 1, and that's the algebra R direct sum R. We could throw in 2, and then you get an algebra which is the 2x2 real matrices. You could throw in 3, and you'd get 2x2 complex matrices. So all of these are also superdivision algebras. You may wonder, why did I stop at 3? Why did I like switch and start going to square roots of +1 instead of throwing in more square roots of -1? Well, the thing is that when you throw in 4, that's too many. So neither Cliff 4, that is where you throw in 4 square roots of -1, nor this other guy where you throw in 4 square roots of plus 1. Neither of those is a superdivision algebra. So the buck stops there in a sense, but actually both of them are Morita equivalent to a certain superdivision algebra, namely the quaternions. But the quaternions, you can think of it as a superdivision algebra where every element is even. That's one way you can think of it as a superdivision algebra. So what's this Morita equivalence business? Well, what we care about these algebras are their representations, how they act on vector spaces. And so you say that two superalgebras are Morita equivalent if they have equivalent categories of representations. And superalgebras like to act on super vector spaces. And you can show that Cliff n is Morita equivalent to Cliff n plus 8. So although the Clifford algebras keep marching on forever, getting bigger and bigger, in terms of their categories of representations, they loop around. You get back to an equivalent category of representations after 8. So here what I did is I went almost 4 in one direction, almost 4 in the other direction. But by the time you go 4, throwing in either square roots of 1 or square roots of -1, you get Morita equivalent things. So you get all those, and here they are. So these are 8 superdivision algebras, and these are giving us the Z mod 8 in our previous chart in some sneaky way, and 2 of them are purely even. So here, Cliff 4 is not equal to the quaternions, it's just Morita equivalent to it. The rest of them, these are actually equal to it. I could have written equal, I probably should have. But okay, that's 8. What about the other 2? Well, there are also such things called as complex Clifford algebras, where you start with the complex numbers and you start throwing in square roots of -1, additional square roots of -1. So I've been mainly talking about algebras over the real numbers, but now I'm really here looking at certain algebras over the complex numbers. So Cliff 0 with this fancy C here is just the complex numbers. We haven't thrown in any extra square roots of -1 yet. And then Cliff 1 would be where you throw in an extra square root of -1, and then it turns out that that you get C plus C, the direct sum of 2 copies of C. And this kind of complex Clifford algebra also has periodicity, but it's mod 2 periodicity. So Cliff n plus 2 is Morita equivalent to Cliff n. So you get 2 more superdivision algebras this way, and just for fun, I'm drawing it as a smaller circle inside the bigger circle. That doesn't really mean anything too much, I don't think. And so, right, so we get 3 purely even superdivision algebras, which are our good old friends, the division algebras, R, C, and H. And then we get these other ones that are only superdivision algebras. And so the remarkable fact is that these 2 groups of 10 things that I've described actually do correspond to each other. I may have bamboozled you into thinking that they do, but I hadn't actually shown it yet to you, and it takes some time to show it. So I'm claiming that there's a specific God-given one-to-one correspondence between the first thing I showed you, the 10 different ways that unitary or anti-unitary operators can commute with an irreducible unitary representation of a supergroup. I should say Z mod 2 graded group. That's what I meant to say, on a super Hilbert space. And the 10 superdivision algebras. I did sort of sketch out why the 10 superdivision algebras correspond to the 10 Morita equivalence classes of real and complex Clifford algebras, because the way I presented you these superdivision algebras is I described them as being Clifford algebras. But it should still be mysterious in your mind why in the world it worked out that way. Why, starting from superdivision algebras, should you be inevitably led to be thinking about Clifford algebras? In physics, we like to think about Clifford algebras because representations of Clifford algebras give you things called spinners or pinners, which are ways to describe things transforming under the double cover of the rotation group. So it's very important for studying things like spin 1/2 particles and spacetimes of various dimension. But when we were talking about superdivision algebras, we had nothing about that on our mind. And so it's mysterious that Clifford algebras show up. So Wall's paper, I think in 1964, about this subject, he shows why they are connected. But the proof of the connection is pretty complicated. I wouldn't say we have a good reason, simple reason why there is that connection. And I don't think we've exploited it fully yet either. This other connection, the first item being connected to the other two, I'll say a word about, but it also takes some work to show. But in any event, we get this set of 10 things, and I call that the Brouwer-Wall monoid of R. That would be most illuminating to you if you had heard about Brouwer groups, which are groups connected to division algebras over a field. It's the group of Morita equivalence classes of division algebras over the field. It's called the Brouwer group. And then Wall generalized it to the super context and got a Brouwer-Wall group, so people call it. But here, this 10 here is not a group. It's a union of two different groups, and it's a monoid. Here, anyway, to finish off, is the correspondence between the superdivision algebras and these different ways that a representation can commute with even or odd anti-unitaries. And so the kind of thing you have to do to establish this correspondence is to say, suppose I have a super Hilbert space on which I have an even unitary T that squares to -1 and an odd anti-unitary C that squares to -1. Given that, I want to make my super Hilbert space into a module into a representation of the Clifford algebra CLIF3. I want to show that I can get CLIF3 to act on that. That's how the correspondence goes. And so you have to fiddle around with these operators to get to show that you can get CLIF3 to act on it. Or conversely, given that CLIF3 is acting on your super Hilbert space, show that I can cook up operators T and C. So I know how to do that, but I only know how to do it in a very pedestrian way where I just go, oh, you do this and this and this and this and this. So I don't want to tell you that for 10 different things because it would bore the hell out of you. So there's probably some better way to think about this that lurking out there waiting for us to discover it, but I don't know it yet. So this is a really interesting pattern in mathematics that shows up in physics, and I really haven't even skimmed the surface of it, especially if you read about it in papers on condensed matter physics, you'd see a completely different aspect of the story where they dig into how you actually build Hamiltonians that give you physical theories that have each of these 10 possibilities of symmetry. And they build those Hamiltonians using fermions, and those fermions they describe with the help of these Clifford algebras. So that does provide a bridge between the symmetry description and the Clifford algebra description that must be a clue as to what's going on. But I, alas, can't talk about that now. So I'll stop here. Thanks.
Thanks, John, for such a wonderful talk. Can I ask a clarification question on your previous slide?
Sure. Hi, Tevian. Tevian is here.
Right. So on the second point, obviously there's Clifford algebras are more general than just the CL0, n Clifford algebras that we considered in your talk. Is the claim, so if you were to have a more general Clifford algebra with CL p q, is the claim that anything like this is going to be sorted into one of the 10 Morita equivalence classes?
Yeah, that's right. So so it turns out that a very general fact about Morita equivalence, let me just remind people what Morita equivalence is, they can stare at this. The general about Morita equivalence is that if you have an algebra, you can form a new algebra, which is this algebra of like k by k matrices with entries in your original algebra.
Right.
And those two algebras that new algebra will always be Morita equivalent to the old one.
Is that the only? Is that the only kind of result from Morita equivalence that you need? Like, is that the only kind of incarnation of it that you need in order to?
That's the main. I mean, there are other kinds of ways that things can be Morita equivalent, but I think that's about all we need for now, right? So if you know your Clifford algebras, you know that like Cliff P plus 1 comma Q plus 1 is 2 by 2 matrix Cliff P Q. So those are Morita equivalent. So that gets rid of all those in a sense if you're just looking for different Morita equivalence classes.
Exactly.
Yeah, that's right.
Okay.
And then and then like this guy is like what is it, 16 by 16 matrices with entries in this guy.
And then 2 by 2.
So that's yeah.
Okay, and another really just quick question or comment actually is just that it actually doesn't seem just looking at the way the monoids are described for the threefold the threefold way and the tenfold way, like the indices were multiplied for the first one and added for the second. So it's just it's not completely obvious that.
I probably should have. I was just being expedient the first time. I guess for the threefold way, I could have copied it, and I would say it's like a disjoint union of Z mod 2 and Z mod 1.
Okay.
So what I had been calling 1 and negative 1 multiplicatively, I could have called 0 and 1 additively Z mod 2. So that would be like the reals and the quaternions, and then the thing I was calling 0 would be an element of Z mod 1. And what's going on there is that of those is the Z mod 2 is called the Brouwer group of the real numbers, and Z mod 1, or the trivial group, is the Brouwer group of the complex numbers. So that is, there's no division algebras over the complex numbers, except the complex numbers themselves, whereas there are two division algebras over the real numbers in which, sorry, I'm not saying this very elegantly, in which the real numbers are all of the center. So normally when people think about this stuff, they split off the real and the complex case, and they get that breakdown of your 3-element set into Z mod 2 and Z mod 1. And similarly here, you get this breakup from thinking about the real and the complex case separately. But the interesting thing is that in this math here, we really want to unify them. We really want to combine them, but that we combine them in such a way that like the complex numbers sort of dominate the real numbers. So like if you add any of these unbolded numbers to any one of these bolded numbers, you get a bolded number. So they both have that. Both our threefold way and the tenfold way had this sort of property that the complex numbers, once they latch onto something, they don't let go.
Once you go complex, so you don't go back.
Yeah, that's right.
Okay, so Tevian has a question, so I'm just going to let's see. Go ahead, Tevian.
Okay, so first of all, thank you, John. That was wonderful. I've got two questions. The first one is the obvious one. What if you drop associativity and the Lactonians into the mix?
I have at times known what all the not necessarily associative superdivision algebras are. That's not quite true. What I've known is what are all the alternative superdivision algebras. What you get, I can't remember it off the top of my head, but the basic idea is that you get the octonions, of course, but then you can get them thrown in various ways. So Todd Trimble at my request, worked out all the alternative superdivision algebras, and so you get a couple more. So like you can see here how like the quaternions could show up in a few different ways. So you get that type of phenomenon with the octonions.
Do you recall how many?
No, I don't recall how many. I should look this stuff up. And I wasn't able to think of anything to do with them at the time. So that would be the thing that would make me like care about it. There should be something fun to do with them.
A possibly related question, is there a relationship between superdivision algebras and things like tensor products of division algebras, as show up, for instance, in the magic square?
Yeah, there has. Well, again, for the non-associative case, I don't know.
I'm happy with the associative case for that one.
Yeah. So what's going on? So tensor products are definitely part of the story here. So what's going on with the way that these 10 superdivision algebras are being formed into a monoid has everything to do with tensor products. So what happens is that, like, how do I add 1 and 2 and get 3? Well, the way I do it is I think of these as superdivision algebras, C and H. I tensor them. Well, I may not get a superdivision algebra always, but I get something that's Morita equivalent to a superdivision algebra. And then I look to see where that one is, and well, it'll be this one here. So yeah, so it has a lot to do with tensoring. But I'll point out that, by the way, that tensoring them as super algebras is different than tensoring them as ordinary algebras, because you stick in extra minus signs in the rules for multiplication when you tensor super algebras.
I think that's where I was trying to go, and you've pointed me. I now know where I need to look to sort it out. Thank you.
Okay, great. Torsten has a question.
Yes. The question is about how what you presented is maybe I'm wrong, but is it connected with K-theory? So the two periodicity is complex K-theory, and the other is the real K-theory, the 8 classes. Okay. My question is then, okay, if we have these 8 classes coming from the real K-theory, I was really amazing because the underlying structure seems to be quaternionic. But from the K-theory, I know that is connected with real vector bundles. Is there anything to understand it? Why I got these quaternion structures, but the underlying structure is in some sense a real vector bundle or something like that?
Yeah. So if you let's see, it'll take me a while to gear up a response, but so no, it's fine. But while I'm doing it, I'll just tell you that, like, if you like read the works of the masters on K-theory, like their books by Atiyah and separately by Baez on K-theory, they actually, I believe, do discuss this. So part of the idea is something like this, that quaternionic vector bundles do show up in real K-theory. And so if you look at, real K-theory has this period 8 phenomenon, for example.
Yes, yeah.
But if you, sorry, let's see, what do you add the dimensions? So if you so it turns out that, like, okay, what am I saying? Quaternionic vector bundles are showing up here. In some sense.
Okay.
And so, for example, if I have 2 quaternionic vector bundles and I tensor them, that does not become a quaternionic vector bundle again, naturally.
Okay.
But what it becomes is a real vector bundle. And so that's related to the fact that 4 plus 4 equals 0. And so they do deal with this in much more careful way, and they basically think about vector bundles with representations of all the different Clifford algebras on them. And so that's one way to think about real K the periodicity of real K theory.
Ah,
So
okay,
don't
okay.
think about real vector bundles, but think about all these Clifford algebra bundles. I'm
Okay.
thinking it all as clearly as I would like, because I haven't been thinking about it so much lately, but that is definitely going on in this subject.
Okay. So something like that. The SU2 is a real form of SL2C and such things is behind that approach. Okay. Second question is about you spoke about these condensed matter phases. As far as I know, I'm not really an expert, but what they used is they assume a weakly interacting system, and because of that, you have Morita equivalence. Did you maybe know a little bit more about the case when the interaction is maybe not weakly? So maybe one lost the Morita equivalence, and then one don't have a tenfold way, or isn't it? Or did you know something about the other cases?
I don't know enough
Okay, so thanks.
about that, but I mean,
Yeah.
I will say that the interesting thing is that this classification in terms of symmetries that
Yeah.
a system may or may not have, I mean, that classification doesn't really care much at all about the details of your Hamiltonian. You can just take any Hamiltonian and you can inquire, do you
Okay.
have
Yes.
symmetry? So I'm just sort of making up this answer, but it suggests to me that there should be some more robust or more general classification of systems without assuming that they are, free fermion systems or close to it. But most of the work detailed work has been try to find free fermion systems that have these various types of symmetries. So
Okay, thanks a lot. Thanks for
sure.
the nice talk.
Thanks. Cohl, do you want to call on people or?
Yes, yeah, I've got it. So Zira, please go ahead.
You're muted, I think.
I think you should be unmuted.
You're not muted, Zira, but I can't hear you, unfortunately.
Can you hear me?
There we go.
Yeah.
Okay. First of all, I'd like to thank you for very nice talk. I have two questions. In relativity, space and time are intervened, but only time reversion invariance is used in tenfold way. Why parity is excluded?
I should say that this although I call this thing T, I'm really not thinking of it as time reversal. So time reversal could be an example of so if I was a condensed matter physicist, then I think your question would be an excellent question. So condensed matter physicists should indeed study a more complicated classification where they think about C, P, and T symmetry for their systems. So I mean, and so you would get a more complicated classification, I believe. So I agree with you. I would agree with you in that sense, that their tenfold way should just be the beginning of a more complex classification. Here, I meant to emphasize it, but I didn't quite emphasize it. Although I started out thinking of T and C as time reversal and charge conjugation symmetry, this result here is a purely mathematical result that does not have anything to do with time reversal symmetry or charge conjugation symmetry. I'm just calling these even unitary operators T and these odd ones C, because that's the way they show up in condensed matter physics.
I see.
Yeah.
Okay.
So like if you had some other opinion about what you wanted to do with these operators, then you could call them something else.
Okay, and the second question is the following. Is there any connection between superdivision algebras and Cayley-Klein geometries?
Sorry, what geometries?
Cayley-Klein geometries. You know, in plane, there is, for example, 9 Cayley-Klein geometries.
Cayley plane geometry?
Cayley-Klein geometries.
I'm sorry, I don't know about that. What I know about are the that there are these 10, there are 10 families of compact symmetric spaces, which are connected with these 10 things. But it sounds like you're talking about something slightly different. I don't know this classification of 9 things that you're alluding to. So sorry, I can't help you. I'll have to find out about that.
Okay. Thank you again. Thank you.
Sure.
Sukriti, go ahead.
Hello.
Hi.
So thank you for this talk. Yeah, so I had this question in one of your earlier slides. You said that there's a possibility that the system might have either C symmetry or CT or T, like
Right.
there were various possibilities. So
Yeah.
there was one of them which was CPT, but that can't be an option because I mean a CPT symmetry is supposed to be there in every physical system, right?
And if you're studying relativistic quantum field theory, you can derive CPT symmetry from other axioms. So there's a CPT theorem there. But that theorem, I just want to emphasize. So I mean, you're right in that sense that it has to be there for those theories. But I'll just emphasize that that's true for relativistic physics. That you actually use the action of the Lorentz group on to prove that CPT theorem. So I'm not aware of any theorem that applies to, like in condensed matter physics, where you don't have Lorentz symmetries. I don't see why you would need to have CPT symmetry there. I might be wrong, but I think you have much more flexibility in what your symmetries can be in these condensed matter systems, because they don't even have Galilean symmetry, much less Lorentz symmetry.
Okay, I see, thanks. And one more question, a quick one. So about charge conjugation, generally when we talk about it, we say that a particle goes to antiparticle, but in the context of condensed matter, you said that we say that a particle goes to
a whole.
Yeah. So I'm sorry, I was just hearing my own sound.
Yeah.
But a whole, what if the particle is charged and a whole is not charged? So how can a whole be considered to be a charge conjugate of a charged particle?
I mean, most typically, I mean, I guess I could try to imagine an uncharged whole, but typically I should just emphasize that wholes are charged. That is, if you have a crystal and you knock an electron out of one atom, that you get a hole, and that acts like a positively charged thing. And so I mean, so you typically describe holes as positively charged particles in condensed matter physics, and you can have all sorts of wonderful things, like you have these things called excitons, which consist of an electron and a hole orbiting each other, attracted by their electromagnetic field, and so on. Now, maybe I could make up some other kind of hole that wasn't electrically charged if I was smart enough. Condensed matter physicists are very good at doing all sorts of sneaky things, but I don't know about that. But anyway, that kind of, if you were able to do that, that would probably be an example of a system where you didn't have a symmetry interchanging particles and holes, I imagine, because they would be too different from each other. I just guess.
Okay, thank you.
Sure.
Okay, Francis, please go ahead.
Okay, thank you very much, Prof. Please, I wanted to get a little clarity in the direct sum of the Hilbert of your spaces. You made mention of H naughts and H1, where the H naughts are the boson. You specify them to be the boson, and the H1 to be the fermions.
Well, I want to emphasize that's one thing you can do, and I said that that's not what I'm going to talk about. But yeah, so in supersymmetry, that is how you let H0 and H1 be. But I'm saying that you can use these H0 and H1 for all sorts of other things too. And I'm saying that in condensed matter physics, they do something else. They let H0 be a Hilbert space for particles and H1 be a Hilbert space for holes.
Okay.
So
I wanted to add.
The mathematics I'll just emphasize is that you just have you just have a Hilbert space that's the direct sum of two parts. Then it's up to you, the physicist, to decide what you want to do with that.
Have you seen any examples where people have been interpreting this as bosons and fermions? Or is it
in supersymmetry, people often describe Hilbert's do that.
Sure, but I mean in the context of the tenfold way.
Strangely, no. Strangely, I have not seen people on supersymmetry working with the tenfold way. That could easily be just my own ignorance. Maybe I should do some kind of clever text search to find that. But did you have more of a question, Francis, or?
Yes, Prof. I wanted to get a little clarity. With the tenfold ways, you spoke about the real, the complex, the quaternions, and that's the division algebra. And you mentioned the Clifford, the type of Clifford algebra is associated with these things. When I see particles, elementary particles, I normally think of them of some sort of Lie algebras with the Lie algebra structure. So I think of root systems. And when I look at root systems, we have what we call the affine spaces or affine root. What would that come? Where would that come when you have an affine? It's an affine root.
There are different ways to answer that, I guess. So yeah, so in this talk, I was talking about group representations.
Yes.
There would be a whole similar story about Lie algebra representations. So one kind of thing you would do with root systems or affine root systems is you could build a Lie algebra out of it, which would be like a Katz-Moody algebra if you'd had an affine root system. And you could talk about representations of those on super Hilbert spaces, and you could demand a rule like this, but not with group element, but with a Lie algebra element in here. So if you do, and I imagine that you could take an ordinary Lie algebra and think of it as a Z mod 2 graded. I know you can think of it, some ordinary Lie algebras, you can think of them as Z mod 2 graded in various ways, where you take the root lattice and you put a Z mod 2 grading on it. So you just pick a way of saying for each point in the root lattice whether it's even or odd, and it just has to have the property that when you add the correct property, that when you add two even ones, you get another even one, and so on. And then you could talk about Z mod 2 graded representations of those Lie algebras. So that's one thing you could do, and that's I haven't really seen people talk about that much at all in terms of the tenfold way, but you could. There's another thing, which is there's also a whole theory of super Lie algebras, Lie super algebras, that can also be studied using root systems.
Okay, and Prof, with your grading, with your Z2 grading mod 2, addition with mod 2, when you are adding in mod 2, and especially with the Z2 grading, I wanted to know what happens is your Z. What if you consider your Z to be a prime or an odd prime? What happens to such grading?
I don't know quite what you mean, but I could take Z mod P for an odd prime, but then I can't Z mod 2 grade that. There's no consistent way to talk about even versus odd if we're working modulo an odd prime. So I don't can't think of anything that works.
Okay, so John Barrett, you've got a question. I'm just gonna I need to ask to unmute you. So
Yeah, you're muted.
Hi, hello, John. Nice to see you.
Yeah.
Wanted to encourage you to come and give a part 2 and talk about these compact symmetric spaces and the tenfold way of those. That would be nice.
Great. Well, that would be a lot of fun. That's a very fun story. Yeah.
Okay, cool.
Okay, that's a nice question.
that made it. Yeah.
You're not asking me to tell it to you right now, I assume.
Okay, that might actually be a good way to end things off, unless if there's anybody else out there who is brave enough to ask a question.
That's a way to scare them. Who among you is brave enough? Okay, Michael.
Michael is brave enough.
Thanks for giving me the chance. I just don't know. Oh yes, here is here. I show my video too, as I'm honored to ask a question. I saw your paper about homotopy hypothesis, and I thought if there is a way to relate this category theoretic construction to what you are doing here, and perhaps even relating it to what Cohl did in her video lectures, where she tried to include the Octonian perspective. Is there a way to find a way to link them all together from such a Grothendieck'ian perspective?
Well, I certainly, that's a very big question. So I'm certainly hoping to do ambitious things like that. I'm just not there yet. The connection that was mentioned between this tenfold way and K theory connects it to homotopy theory in some interesting ways. So I think I can get some very nice connections between this and homotopy theory. As for the octonians and the non-associative superdivision algebras, I really don't know how they fit into this story at all. So Tevian already asked me about the non-associative superdivision algebras, and my friend Todd Trimble figured out kind of classification of the nicest ones of those, but I just haven't figured out anything good to do with them. So I would urge people who love the octonians to try to figure out something good to do with the non-associative superdivision algebras.
I like the way Cohl related this to compositions of maps in her videos on this course page, and so I thought maybe this would be like a way to make them in a way associative, and maybe have this procedure related to chain complexes. So maybe if you didn't look at the videos, I think they are really very, very nice. They are listed on the page which accompanies these sessions, and I enjoyed them very much. Unfortunately, it's the first time I realized there is this series. And thank you very much for your paper on the homotopy hypothesis, which is kind of so intuitively related to this process of composing maps. That's how I came to ask this question, possibly relating your positions. Thank you. I very much enjoyed your presentation and the videos, and so thank you very much for this great opportunity to learn.
Great, thank you very much.
Okay, thank you.
Couple more questions.
Yeah, a couple more questions. Yeah.
Francis?
Hello. Yes, hello, Prof. Please, I wanted to ask this last question: that would the tenfold also work for the case of isospins? And when you talk of when the Higgs boson, will it work for that case?
Will what work for that case?
The tenfold algebraic structure work for isospins?
Yeah, I mean, this math of the tenfold way is extremely general, so it works whenever you have any group acting on a Z mod on a super Hilbert space. So you can always, so you take, so pretty much any physical theory that you can think of will have some group acting on some Hilbert space. And if it's just a Hilbert space, then you get the threefold way showing up. But if you're able to break your Hilbert space into two parts and have the group either preserve or switch those two parts, then the tenfold way springs into action. And so that's very general. So I'll leave it up to you to apply it to the standard model. Yeah.
Thank you.
Okay, and we've got a question from Prof. Dobrev. Just one sec here. And we can ask to unmute you. There we go. Go ahead.
Hello.
Hello.
I missed the beginning of the talk. Maybe you mentioned also this tenfold way by the way these are described by the 10 real simple algebras or groups. Now the question is, what about if we enlarge the family to superalgebras? They appear in your exposition in another way, but
Yeah.
in view of this,
Yeah. Right. So alluding to some other tenfold
algebras
that I've seen of real simple Lie algebras.
What is the answer to the super case?
I have no idea. The answer is that I don't know. Sorry, I was just telling people that he's alluding to like another kind of tenfold way. I don't even understand exactly how that tenfold way is connected to these tenfold ways that I've been talking about. But so I'm not ready at all to think about how it would generalize to these super algebras. But it sounds like a worthwhile thing to think about.
If somebody wanted to look up this other tenfold way, is there what would you type into Google? Is there a name for it?
I've seen one paper about it, and you know who it's by? I forget who it's by. For all I know, it's by you. Yes, I could dig around, Nichol, but I can't.
In the table I'm talking about is in one of your papers.
My papers?
Yeah. Okay, maybe it's just quoted there, but it is. I actually saw it first time in this paper of yours.
I don't even know which paper you mean. I must be getting old and senile if I'm writing papers. I don't even know what they are. So anyway, I'll attempt to find out. But I was looking at a paper. It was definitely by somebody else, Cohl, that listed this other tenfold way and was trying to relate it to.
I can put the link and put it in the link here. But
Yeah,
I don't know
sure.
how to do it actually.
Yeah, I think the chat might be off on this version of Zoom, but
there is no chat. Okay.
If you could, if you could,
I can send it by
email me. I would really appreciate it.
email.
I'm curious to know what you're talking about. Thank you.
I'll send it by email. Yes.
Okay. Thank you. Thank you so much. Okay, so one more question here, Christopher. Go ahead, Christopher.
Oh, thank you. Yeah, and thank you for this great talk. I had a question here about, you've got these three, well, two monoids here, the -1, 0, 1 monoid for the threefold way, and this 10-element monoid for this tenfold way. If you go to the alternative algebras and you have a similar diagram to your circle, what is that monoid, and how many elements does it have? Or is it a monoid? Is there this kind of similar graded structure for representations? And what is that? I wonder.
I don't know. I don't know. I don't even know if it works. So like if I tried to understand that, I would start by thinking about the non-super case, like where we think about just plain old division algebras, and then what's going on in the threefold way. One way to think about it, really, it's disguised here, is that if I like tensor the quaternions with the quaternions, I get an algebra that's I guess it's 4x4 real matrix algebra, and that's Morita equivalent to the reals. So that explains me why -1. That's what matches -1 times -1 is 1. If I tensor the octonions with the octonions, I know very little about the representations of that I don't even know if I know what a representation of a non-associative algebra is, for starters, okay? And then I don't really know much about the octonions tensor the octonions. So I get stuck trying to do things there. I mean, it might be fruitful, but it would definitely require like some hard thinking to get anywhere in that direction.
Okay, so it looks like Dobrev may have one more question, and we can close. I don't want to I don't want to keep you here forever, but well, I wouldn't mind, but I'm sure you must get tired at some point. So I'm just going to see if that was a question or not.
Do you have a question, Dobrev? Sorry, I don't know your first name.
Yeah. So I'm pressing ask.
He just left his hand up. Oh,
I'm sorry, maybe I didn't. No.
Oh, it's not another.
No,
it was just your hand up from before. Okay, that happens. No problem. Okay. Yeah. All right. So in that case, this will be a good time to close things off. So thanks again, John, for such a wonderful talk. That was really clear. In fact, I had some clarification questions that you ended up kind of clarifying when you actually gave the talk. And yeah, so thank you for giving such a clear talk. That was also really interesting. You know, we'd of course be very happy to have you here again anytime. And yeah, thank you to everybody for showing up, for your enthusiasm and your questions. So in our next talk is scheduled in 3 weeks on the 27th of February, 4 p.m. Berlin time. That's earlier than usual. We have Professor Balachandran from Syracuse University speaking to us about a paper he wrote entitled The Gauss Law, A Tale. So thanks again, John, for giving such an exceptionally interesting talk. Thanks everybody for showing up, and you know, we'll see you next time.
Yes, thanks to everybody.